getting the fall colors here. Very spectacular view from the air, but not much to look at in the sky. So we're going to go ahead and take a look at the surface chart and see what we got going on. Got a series of progressive weather systems coming out of Canada. One made its way overnight through the Great Lakes up into Quebec. And here comes the next one. This is an Alberta clipper coming out of Alberta with cold air sweeping through North Dakota and Montana with some snow showers. That's being driven by this weak 1023 millibar high up in Alberta, and that represents cold air that's pushing back behind that low pressure system. And in the eastern U.S., we have plenty of tropical moisture. Dew points way up there from the upper 70s in Florida to 63 at Boston. And even in the Canadian Maritimes, temperatures are up in the 70s. Pretty unusual for November. There's a look at our 250 millibar upper air chart. Definitely got a strong polar front jet out there in the northern Pacific. That's still a ways from the west coast, but we're probably going to be tangling with that in a few days. The main polar front jet running from northern Arizona up to the Great Lakes. And it looks like we've also got a subtropical jet to throw into the mix. Large long-wave trough dominating the western U.S. and a long-wave ridge out east. And that tells us that there's a fairly substantial amount of cold air in Canada, in the northern Rockies, and maybe into the central Rocky region, and warm out in the western U.S. And we've seen that with the temperatures in the Maritimes and the dew points almost tropical all the way down the east coast. And just to kind of complicate things, we've got Tropical Storm Eta coming onto the western Florida coast. That storm is actually kind of a distraction today. We're focusing on dynamics, and there's quite a few YouTube streams out there that cover the tropical stuff, so we're not going to focus on that, but just the important details. 60 knots, that's going to be up near hurricane strength, but 990 millibars, that's not very deep. The track is taking that up north of Tampa as a tropical storm, making landfall sometime late tonight or tomorrow morning, then crossing during the day towards Jacksonville tomorrow evening. Storm surge will be up to 3 to 5 feet around the Tampa Bay area. That'll probably be the main danger. And of course the wind field coming inland with some sporadic damage here and there. Florida is definitely used to that with the weaker hurricanes. And of course this is just a tropical storm. But we are looking for some flooding risks. Marginal across much of Florida, but they've got a slight category from Tampa all the way down towards Fort Myers. So let's take a look at that front. We're going to look at the air mass on either side. We're going to look at Jacksonville this afternoon and Memphis. So what does it look like in Jacksonville? Let's take a look. There's our skew-t. This is all a tropical air mass, and the lapse rate is weak to moderate. In other words, it kind of leans towards the left like that. Now there's a couple of ways that lapse rate can be set up. If we take kind of like a sample and look at how much it leans over. If it leans like that, it's isothermal. In other words, the temperature is the same as you go up. It has that same value of 10 Celsius. If it leans this way, that indicates an inversion, a true thermal inversion. So the temperatures are rising through that layer. But if it leans over this way, it's got a weakly positive lapse rate. And the more it leans over, the more steep the lapse rate. And that's about the maximum right there that we're going to see. So this lapse rate right here that falls kind of in here, that indicates a moderately positive lapse rate. And that's typical of what we find in the tropical air. We also see a lot of moisture. That's the influence of all the evaporation in the tropical regions and advection of that moisture northward. Now let's take a look at the other side in Memphis. Looks a little bit different, doesn't it? Well, if we compare it, everything from here upwards is going to be similar to Jacksonville because that's all tropical air. It's going to have the same temperature characteristics and similar moisture characteristics. But down below, we've got cold air. The homogeneous cold air mass itself is located down here. Now you notice that we have a steep lapse rate. That's due to modification of that air mass. But above that, we've got this thermal inversion. See that slope right there of the temperature line? It kind of goes up like that. That's a true thermal inversion. And then above that, we've got kind of a weekly positive lapse rate, kind of running about like that. Now, this whole layer in the transition zone is referred to as the frontal inversion. A very important distinction is that does not have to be a true thermal inversion. A frontal inversion can be a true thermal inversion, it can be isothermal, or it can be weakly positive as far as lapse rates. In other words, that right there, that's a weakly positive lapse rate, and that can be part of a frontal inversion. Now the moisture is the other aspect. You see the green line right here, and notice how it follows the temperature line up through the frontal inversion. That's a classic signature of a frontal inversion. And that indicates that we're passing through a frontal inversion, and then everything above that, that's going to be the frontal surface right there. See, if we go back to this diagram, there's the transition zone. That's going to have a thermal inversion, or it's going to be isothermal, or it's going to be weakly positive lapse rate. Then above that, the frontal surface, and then tropical air. Below it, the bulk of the cold air, and at the very lowest levels, we can have a steep lapse rate, unstable conditions within that thin layer there due to modification. And you can get mechanical turbulence and gusty winds, cumulus towers, that kind of thing going on if there's enough surface heating or if you have warm ground. Now, typically the moisture line follows the temperature line through a frontal inversion, but not always. One example is Detroit. Michigan has had this area of subsidence. We're looking at the water vapor imagery. The yellow is indicating subsidence and sinking motion, dry conditions, and you can see how much of that has been working on Michigan. If we bring up a skew-t for that area, well, everything up to here is the frontal inversion, but we don't see the classic signature of the moisture following that temperature line. And that's indicating we've had very strong subsidence, adiabatic warming, drying, working on the air mass. And this frontal inversion kind of doubles as a subsidence inversion. And if we look at the moisture, you can see how with height that spreads away from the temperature line instead of following it. So it doesn't have the classic frontal inversion signature. It resembles a subsidence inversion. And with the temperature line and dew point line being far apart in the mid-levels, that indicates that there's very low relative humidities in that layer. And this is not too different from the loaded gun that we see on the Great Plains in the springtime. If it was a little bit warmer, I would probably refer to that as a loaded gun. You know, we really would need more instability in the upper levels, more of a steep lapse rate. Well, there's an example of a loaded gun from 2 years ago. You can see the dry conditions in the mid-levels. That's not due to subsidence, really. It's more due to advection of hot air from the interior regions of Old Mexico and New Mexico out over the Great Plains. So the end result is something that looks like a subsidence inversion with the moisture line and the temperature line being far apart, but it's more due to advection than downward motion. But that's not what we have in Michigan today. So the cold front, the location is found on the leading side of a transition zone. In this case, we know that the transition zone is where cold air is replacing warm air. So temperatures are going to be falling across that transition zone. If it was the other way around, we would have a warm front, but we're focusing on the cold front. So the cold front found on the warm side of that transition zone, that right there is the transition zone, and then the bulk of the cold air is located back in here. We always find the cold front on the warm side of that transition zone, not within it, not on the back side, but on the leading edge. That's very, very important. And you notice that I kind of avoided this area here. That's prefrontal convection. It's probably laying down a cold pool there in the Appalachians. With thickness, same thing. There's the thickness lines, the red dashed lines. They're packed on the cold side of the front within the transition zone and back into the cold air, but there's very little of the thickness lines out in the warm air. Moisture discontinuities. Yep, not always, but frontal passage can be marked by a moisture discontinuity. Here the front, located right there, and you can see that drier air working into the backside. That's a possible indicator of a front, but that is not the indicator of a front. Also the wind field. Typically the wind field on the cold side of the front represents the northerly flow back in the cold air mass, and then on the other side there tends to be a southerly component. Again, that's a indicator of a front, but not the indicator of a front. You always got to go back to temperature. Now we often see certain pressure changes around a front. The front located right there, you can see that on the warm side, these pressure tendency values show mostly a falling trend. On the other side, we see mostly a rising trend, especially in Indiana and Ohio. That's not always a firm indicator of a front, but that can clue you in further where it's located. All right, so a quick update on Tropical Storm Eta. We've got spiral bands coming ashore. There's one right there. Looks like another wave coming inland. And we've always got to be concerned with the left forward quadrant of a landfalling hurricane or tropical storm, because that can be a potent area for high SRH, high storm relativisticity, and rotating storms. So there's Tropical Storm Eta coming on shore. If we pull up a random forecast skew-t, say right there, we see that there is substantial 0 through 1 kilometer shear. There's the 0 through 1 kilometer shear line, the storm motion located right there, and that sweeps out a very large area on that photograph. And that indicates high SRH values, 200 to 300, which is enough, more than enough for rotating storms. Another sample, let's go out east of Tampa, and we see substantial 0 through 1 kilometer shear, high SRH. So any storms that get going along these spiral bands will have the potential to rotate. And not surprisingly, we do have a tornado watch box in effect from Tampa all the way through Fort Myers. I would not be surprised to see 1 or 2 more boxes issued later this afternoon, further towards the northeast. And that'll do it for this edition of Forecast Lab. I hope you enjoyed the dynamics lessons. I'm going to take a look at the numbers, the viewer numbers. If they start falling off as the week goes on, I'm going to assume that the content is too dry. If they rise, we'll do more of these. So if you want to see more of them, please spread the word and post on your social media about them. And we'll see how things go. Anyway, take care. We'll see you tomorrow for another edition of Forecast Lab. Bye-bye.